Welcome! Today we are examining adaptive hierarchies, focusing specifically on splay trees. Unlike static structures that force data into rigid shapes, splay trees are self-adjusting mechanisms that optimize themselves based on how data is actually accessed. We will explore their mechanics, mathematical proofs, and their role in memory management. Part 1. The evolution of self-adjusting data structures. To understand why splay trees exist, we must first understand the history of latency minimization. Data structure engineering is essentially a history of fighting latency. In the early days, memory space was the bottleneck. As hardware evolved, the bottleneck shifted to access speed. While rigid structures like ABL trees solved the worst-case search problem, they ignored a crucial reality. Not all data is accessed equally. A standard binary search tree has a fatal flaw. If you insert sorted data, it degenerates into a linked list, causing linear access time. Rigid structures like red-black trees fix this by enforcing balance invariance. However, they treat every piece of data as equally important, expending energy to balance nodes that may never be accessed again.
This static approach contradicts empirical reality. Real-world systems, from virtual memory to web caches, exhibit locality of reference. Specifically, temporal locality means that if you access an item now, you are very likely to access it again soon. Static trees are blind to this pattern.
Enter the splay tree. It discards explicit balance metadata, like colors or height counters. Instead, it uses a simple heuristic. Whenever a node is accessed, it is moved to the root. This guarantees that frequently accessed elements naturally stay at the top, offering an amortized cost of big O of m log n over a sequence of operations.
Part 2. Architectural mechanics. How exactly does a splay tree move a node to the root without breaking the logarithmic time guarantee?
A naive rotate-to-root strategy fails to balance the tree. Splaying uses three specific primitives. The zig is a simple parity fix. The zig-zag handles bent alignments, similar to AVL double rotations. But the critical innovation is the zig-zag step for linear chains. By rotating the parent with the grandparent first, we halve the depth of the access path, flattening the tree. There are two ways to implement this. The classic bottom-up approach requires a stack or parent pointers to trace the path back up, which increases memory overhead. High-performance systems, like kernels, prefer top-down splaying. It restructures the tree during the initial search descent, requiring only constant extra space and improving cache locality.
Splaying isn't just for lookups. It powers all dictionary operations. To insert, we splay the nearest neighbor and split the tree. To delete, we splay the target to the root, remove it, and then join the remaining subtrees. These operations are intuitively handled through the splay primitive itself.
Part 3. Mathematical foundations. The efficiency of splay trees is proven through amortized analysis. We use the potential method to analyze cost. We assign a potential energy to the tree based on the sum of the ranks of its nodes. A tall, linear tree has high potential. Splaying a deep node reduces the tree's height, drastically dropping this potential. This drop essentially pays for the expensive rotations, balancing out the cost equation.
The central theorem is the Access Lemma. It states that the amortized cost of splaying a node x to the root t is bounded by 3 times the difference between the rank of t and the rank of x, plus 1. This proves that the cost is logarithmic with respect to the total weight of the tree. This math leads to powerful properties. Static optimality means splay trees match the performance of ideal static trees for specific frequencies. The working set theorem proves they act like LRU caches. The scanning theorem shows that accessing nodes in sequential order takes linear total time, effectively constant time per item.
Part 4. Systems applications. How are these trees used in the real world, particularly in operating system kernels?
Historically, kernels like FreeBSD used splay trees to track virtual memory areas. Since programs tend to access memory addresses in clusters, splaying the accessed memory region to the root made subsequent lookups nearly instantaneous, exploiting the natural spatial locality of process memory. However, there is a trade-off. While splay trees keep hot nodes in the CPU cache, every lookup involves rotating nodes, which are technically memory write operations. In multi-core kernel systems, this triggers the cache coherency protocol. It forces other processors to invalidate their caches and reload data, causing significant traffic on the memory bus.
Part 5. Concurrency and Modern Adaptations. The rise of multi-core processors presented a major challenge for splay trees. The fundamental problem is that in a splay tree, a read is actually a write operation because it modifies the tree structure. This requires exclusive locking, which serializes access. As CPU core counts increased, this global lock became a bottleneck, forcing systems to migrate to red-black trees. To survive in concurrent environments, we use techniques like lazy splaying, where we only partially rotate nodes or wait for a threshold before modifying the tree. We also see attempts at relativistic splay trees, which use complex copy-update mechanisms to allow wait-free reads, though these are difficult to implement. Part 6. Applications beyond the kernel. While they left the kernel, splay trees thrive in user space.
In user space, they excel. Network routers use splay trees to handle bursty packet trains. Data compression algorithms use them to create adaptive prefix codes on the fly. They are also used in garbage collectors and to emulate LRU caches in memory-constrained embedded systems.
Part 7. Comparative analysis. When should you actually use a splay tree? Let's compare the splay tree against the industry-standard red-black tree. Splay trees win on locality and storage overhead, requiring 0 extra bits per node. However, red-black trees offer strict worst-case guarantees and, crucially, support excellent concurrency because lookups don't modify the tree.
The decision comes down to your data distribution. If your access pattern is uniform and random, use a red-black tree. But if your data follows a Zipfian distribution, where a small percentage of items are accessed most of the time, splay trees can be 2 to 5 times faster.
Part 8. Conclusion and Key Takeaways.
The splay tree remains a masterpiece of algorithmic design. It serves as a powerful locality engine for non-uniform data and offers code simplicity. While concurrency issues have pushed it out of modern kernels, it remains the optimal choice for compression, routing, and any domain where the future is unpredictable, but locality is guaranteed.